Now let's talk about drag.
There are a few different kinds of drag. We have the parasitic type drag, which is form drag, skin friction drag, and interference. So this shows how parasitic drag is increased as an effect of speed or a result of speed. And we're going to take a look at more of that information in just a second. Let's now go into how you actually take a look at how object shape affects coefficient of drag. So if you're looking at airflow this way, a flat plate has a pretty large coefficient of drag. It just slams against this. Some air probably comes out to the side. It'll curl around and create all these vortices. So depending on the streamlined shape, you're going to get a lot larger coefficient of drag. And some of you tested that out with the air or the wind tunnel last year when you milled out wooden cars. So we're actually going to check that out a lot more this year with airfoils and actually create our own airfoils. And you can see that the coefficient of drag for this is significantly less than even that of a bullet, which was sort of the shape of our cars that we created. So now we're going to get into the specifics of different types of drag. Form drag is just the result of turbulent wake behind the object. So as air moves around it, then on a flat plate, this blue is just the turbulence here. So the silver is the flat plate. So we have turbulence here, we have a high pressure in the front and a low pressure in the back, so that's where you have a lot of turbulent flow. On a cylinder, there's a lot less turbulence. There's again a high pressure in the front and then it curls around in the back. On a streamlined shape, there's, according to this one anyway, there's only 10% of the form drag on this flat plate. So there's a bit of a high pressure in the front and it really follows this surface quite well. So form drag is a lot less of an issue in a streamlined. Now skin friction drag is another one that we had just talked about, and that's where you have this boundary layer that causes more turbulence. So again, Howard Hughes was one who really was the first to recognize that and do something about it by making a smooth surface and replacing those rounded rivets with flat embedded rivets. And so that makes a big difference on the wing surface and reduces that boundary layer turbulence by quite a bit, which then reduces drag by quite a bit. Interference drag is a result of varied air currents interacting over the wing. So if you have some imperfections or insects or ice buildup on the wing, then that can cause air currents that are turbulent up high, and then you can see how that sort of spreads out in this type of shape here. And so normally you would get some more turbulent air on the back half of the wing, but now you're getting it a lot further up, and you're getting actually, instead of just a streamlined shape, it's sort of this triangular shape. Now again, think back to your gliders. That's why we have a lot narrower wing, a lot thinner chord here, so that we have a lot less of this turbulent drag and a lot less boundary layer effects on that. And then induced drag is drag created by the change in pressure from the upper and lower surfaces of the wing. So if we look at induced drag, as you get going faster and faster, induced drag is actually going to reduce. Those pressure differences are going to create a lot less drag. Parasitic drag increases as you go faster and faster. So there is this point of minimum possible drag at this optimal speed. So there is an optimal speed for every particular aircraft at its and its airfoil going a certain speed. So let's take a look at the drag equation. So again, drag is determined experimentally, and it's a lot of factors: shape, angle of attack. So this right here is your equation. Coefficient of drag is 2 times the value of d, the drag, divided by the area of the wing times the density times velocity squared. So go ahead and pause this and write that down. So if we're going to apply this, we have the same Cessna from the previous example. It takes off under the same conditions. How much drag is produced when the wing is configured such that the coefficient of drag is 0.05. So how much drag is produced? How many newtons of drag if the wing has a coefficient of drag of 0.05? So if we're going to figure out how much drag, we know CD. So what I would suggest you do is write down CD equals, and then A equals, rho equals, V equals. Identify all your variables first. And then if we figure out what D equals, we can just rearrange the equation. So we're multiplying by A rho V squared on both sides. It moves it over here. And then divide by 2, so the 2 is in the denominator. So we end up with this equation here. you might want to review that if that didn't quite sink through the first time, or call me over and I can help. So once we plug in all of these numbers, then we get coefficient of drag was 0.05 times area times rho times v squared over 2. We get a drag of 436 newtons. So what does that tell you? Well, if you have a drag of 436 newtons, your thrust has to be at least that much to maintain speed. If it's more than that, then you're going to be going faster. If it's less, then you're going to be going slower. And the last thing we'll take a look at is downwash and wingtip vortices. So there is a pressure difference at the wingtips. When you have your airplane at the wingtips, the air is being pushed down, and because it's being pushed down and back, it starts to swirl up. So you have this constant swirling at the edges of your wingtips. So they flow out and then up again. They kind of swirl up, and that's what forms that vortex. That resulting vortex does decrease lift and increase drag. So as this plane is flying in this direction, the air spills down over the back, and as it's pushing down, it pushes the other air around it up, and then that kind of fills in that space. So we're getting all these vortices coming down and back, and that's one big reason why they have wingtips. So that kind of prevents a little bit of that and prevents that downward, or that air flowing up and then back down and swirling. So here's a picture of what it actually looks like. As you go by it, then all of these vortices are created. You can see this slice through the cloud. So again, winglets are used to limit those vortices and improve fuel efficiency. And now we're finished.